Hi everyone. So today we'll start the lecture with testing the equipment. It's kind of a quiz, but it's not going to be graded. I know there were some problems with speaker registration yesterday. The site didn't work. Today you should be able to register the speakers, and some of you I know already registered the speakers. So I want just to test the equipment. I was told that before you start actually answering the question, you should do some setup with the speakers. You should long press the power button on your the on-off button, long press the on-off button, then press A, then press B. This will set the frequency to something AB. So we can install it now, and then we'll start the actual code. Once again, it's power button, one click, then A, then B. So I think I just started the collecting the results. So yes, we are collecting opinions, and mostly correct opinions. So let's wait a little bit until the numbers stop going up. This is not going to be graded, it's just the test of the equipment. So I'll probably stop it right now. And we did collect the correct answer is C. Let's look at the question. So the question was, here are triples of vectors, which triple is triple of parallel vectors. Well, we should recall that parallel vectors are just vectors which are multiples of each other. When you look at the triples, well, the first triple, there is no way to multiply 1, 0, 0 by something like something with 0 in the first place and non-zero number in the second place. So these two vectors are not parallel. Second one, once again, to get say this vector from this vector, we should multiply the first coordinate by 1, and we should multiply the second coordinate by -1 by different numbers. Well, here you see that these three vectors are indeed multiples of each other. The second vector is the first one multiplied by -2. This one is the first one multiplied by 3. Well, these vectors are obviously not parallel. To get, say, 4 from 1, you should multiply 1 by 4. To get 5 from 2, you should multiply by 5 halves, different number. And here, well, the first two vectors are parallel to each other. This is one half of that one. But this one is not parallel to either one of those. This vector is not 3 times this because of this minus sign. Okay, so I hope the system will work. Yeah. The question, well, yeah, I can post it. Yeah.
Does it matter if we did what he told us and it didn't work out? Because When the vote goes in, usually it's a green light, right? And then it goes to red
Yes.
light. So,
Well,
and that's what I'm saying.
maybe come to the lecture and we'll see how we can fix it. So I hope the system will be working, and we'll usually start the lecture with a short quiz like this, and then how long it will take, like 2 minutes, 5 minutes, something like this. Please do register your clickers on the website on Connect. There is a link to clicker registration. Well, and let's turn this off. Let's start the lecture.
Oh, this one doesn't work?
So, last lecture we talked about the three-dimensional space, we talked about points in three-dimensional space, we talked about vectors, arrows in three-dimensional space. Well, points are fun, but not fun enough. We should talk about some interesting surfaces, interesting geometrical entities in the space. And the first one we are going to talk is just a plane. A plane is something like the surface of a table. You see it. Like, so if it was flat, then the surface of this page. So we'll talk about planes. Okay, so a plane, well, you more or less know what a plane is. Some kind of two-dimensional flat surface like this. You have two points on the plane, and the whole line between these 2 points is inside this plane. So we know what a plane is. The question is, how can we understand whether, well, how to describe a plane by some equation? How to realize whether some given point lies in some given plane? Well, let's make some observations. First observation is, when you have a plane, so if you have a plane, you can define a direction which is perpendicular to this plane. So there is some direction which is perpendicular to the whole plane. If you take a line on the plane, it's perpendicular to this line. And it's perpendicular to each line. For instance, if you have the plane of a stable, the perpendicular direction is the vertical direction. If you have a plane, so if this is a plane, then this direction is perpendicular to the plane. Okay, so let's start something to start with. Given a plane, we can define a direction. A direction, well, we know how to encode the direction. A direction is more or less a vector. Well, not quite. I mean, direction is just a line. A vector is an arrow along this line. So maybe a direction defines several vectors, but we'll just choose one. So we start with definition. A vector which is perpendicular to the plane is called a normal vector. So we produce a vector, kind of arrow. So here's a normal vector to the plane of the board. Here's a normal vector to the plane of the table. Here's a normal vector to this plane. Just some arrow which is perpendicular to the plane. So is this information enough? Can I just give you one vector and let you produce a plane? Well, the answer is not quite. If I just know a direction which is perpendicular to my plane, well, I sort of know my plane. If I know that this is my vector, perpendicular to the plane. I just know that the vector is vertical, hence the plane should be kind of horizontal, parallel to the floor. But I don't really know which plane it is. Is it the floor? Is it the second stair over there? Is it the surface of the table? There are lots of parallel planes. So each vector defines the whole family of parallel planes for which it is have a family of parallel planes, they all share the same perpendicular direction. So here there will be some vector which is perpendicular to all of them. So it's not enough just to choose a perpendicular direction. Not enough to specify a perpendicular direction. We should specify a perpendicular direction and somehow specify among all the parallel planes with this normal direction just one. And usually we do this as follows. So to specify a concrete plane, we can specify a normal vector and a point on this plane. So suppose I want to describe, let's say, a plane at this position. How can I do it? Well, the answer is, first I specify a normal vector. So I tell you, this direction is the normal direction to the plane. It doesn't quite give me the plane yet. I have the plane, which is perpendicular to this vector. I can shift it. Lots of different planes are still perpendicular to this vector. But now if I tell you that this plane must also pass through this particular point, well, I have only one choice. So this plane will pass through this point and will be perpendicular to this vector. So it seems if I give you this information, a point and a vector, I should be able to find out a plane. So let's try. Let's try to find an equation of a plane passing through a point and with a normal vector ABC. So I want to describe an equation of the plane. I tell you what is the normal vector, give you three numbers, A, B, and C. I give you a point on this plane, and I ask you what is the equation of this plane. Well, what does it mean, the equation of the plane? It's some equation which is satisfied for all points on this plane and not satisfied for points which are off this plane. So I want to make sure that every point x, y, z on this plane satisfies some equation. Okay, so let's try. Suppose I have a point in the space, and I want to decide, is it on this plane or is it not? So I give you a point x, y, z, and ask you, is it on the plane or not? Well, what do I know? I know that the point x naught, y naught, z naught is on my plane. And I also know that my plane is perpendicular to some vector ABC. Also, what does it tell me? It tells me that this direction is a direction inside of the plane. From this point to that point, both points, if I want x, y, z to be on the plane, well, this arrow sits inside of the plane. Well, all the directions in the plane should be perpendicular to this direction, ABC. So this should be 90 degrees. Now look, we do know how to write down the condition that this arrow is perpendicular to that arrow. We can use the dot product. So let's do this. I want to write down that the vector ABC is perpendicular to the vector which goes from this point to that point. How can I write this vector? Well, here I write that vector ABC is perpendicular to something, which means the dot product of this something is equal to 0. And how do I find an arrow which goes from the point x0, y0, z0 to the point x, y, z? Subtract, exactly. So I'll just take x, y, z and subtract x0, y0, z0. If I take this vector and I add this vector to the point x0, y0, z0, I'll get this vector. So if I start at x0, y0, z0, moving in the direction of this vector, I'll end up x, y, z. Okay, so if I want my point x, y, z to be on the plane, I want x, y, z to satisfy this plane. The dot product of this vector with this vector should be 0. Okay. The rest is simple algebra. Let's expand everything. So vector ABC should be perpendicular to the vector x minus x0, y minus y0, z minus z0. In other words, ax minus x0 plus b y minus y0 plus c z minus z0 must be equal to 0, or ax plus by plus cz must be ax0 plus b y0 plus cz. So here's an equation of the plane, of the plane. There is only one plane for which A, B, and C, I mean the vector ABC is a normal vector, and the plane passes through the point x0, y0, z0. Let's just understand in general, well, how this thing looks like. A, B, and C are numbers. x0, y0, z0 are also a number. So the whole thing on the right, well, it doesn't involve the point x, y, z. It's just some number which is kind of a property of the plane. So this whole thing is a number. So we can call it G. So we got the following called simple result. Any plane has an equation of the form ax plus by plus cz is equal to d. And not only this, these numbers a, b, and c, they have very, well, geometrically very visual meaning, where the vector ABC is a normal vector to the plane. Okay, so we'll, in 1 second, we'll do some example with actual numbers. But for now, just I'll repeat the logic. We said that if I want to specify a plane, I should specify a normal direction and a point on the plane. Well, then we did a translation of the following sentence to algebra. If you take a point in the plane, well, if you take 2 points in the plane and look at the vector from one to the other, it is perpendicular to the normal vector. Well, this sentence translated to algebra became this statement. And now we say, well, in fact, every plane can be specified in such a way. You can say that it has a normal vector, it has some point on the plane, so it must satisfy some equation like this. Okay, so let's do an example. So, exercise, find the equation, well, an equation of a plane, of a plane, passing through and perpendicular to the vector 5, 1, 5, 2 minus. So I give you a direction, 5, 2 minus 1. I give you a point in space, and I ask you find the plane which passes through this point and is perpendicular to this direction. So maybe suggestions. Yeah.
ABC are known constants, not 5, 2, and 1, negative 1 are ABC.
Mhm.
Those for that equation, so you can kind of plug right in there. For the other 1, 2, and 3, that is the sorry, that's the X, Y, and Z.
It's not
Sorry, that's not Y, and Z, not in there, just 3, right? Or 1.
Yes, exactly. So basically, we'll just, well, we are given a particular instance of A, B, and C, and it's not Y, not Z. So let's just repeat the same argument. I want the vector 5, 2 minus 1 to be perpendicular to the vector which ends up at X, Y, Z and starts at 1, 2, 3. So this is the vector from 1 to 3 to X, Y, Z, and this vector should be perpendicular to 5, 2 minus 1. Well, now just open the brackets. So it's 5 times X minus 1 plus 2 times Y minus 2 minus plus minus 1 times Z minus 3 must be equal to 0. Open the brackets further. 5x plus 2y minus z is 5, 9, 6. Okay, that's the answer. So once again, what I did is just write the following sentence. If you have a point xyz on the plane, then the vector from 1 to 3 to xyz is perpendicular to the vector 5 to minus 1. once you have this sentence, then you stop in the brackets and you get the equation of the plane. Maybe let me show a different way to arrange the solution. First, well, questions about this solution. Yeah?
Sorry, why is it equal to 0?
0. So the dot product of two vectors is 0 exactly when the two vectors are perpendicular to each other. So that's the property of the dot product. And I did want this vector to be perpendicular to this vector which is in the plane.
On the test, can we just start from the third one and use that equation instead of doing all?
Yes.
Can we just use like that equation instead of starting at the third?
You can, but it's kind of remembering it too much.
Okay.
Let me give you a different way to to arrange the solution. So we will say solution number 2, or alternative solution. I'll use a slightly different approach. I'll recall that this sentence, that every plane has an equation of this form, ax plus by plus cz is equal to 0, where a, b, and c is the normal vector. Well, in this case, I know that the normal vector is 5, 2, minus 1. So the plane, the equation should have the form 5x plus 2y minus z is equal to 0. Once again, why? Because every equation of a plane with a normal vector ABC has this form, ax plus by plus cz is equal to some number d. The only question remaining is, what is this number d? Well, but that's quite easy to find out. We know that the point 1, 2, 3 is on the plane. So let's write this down. 1, 2, 3 is on the plane. So if I plug x equal to 1, y equal to 2, z equal to 3, this equation should be satisfied. So 5 times 1 plus 2 times 3, 2 times 2 minus 3 must be equal to d. So what does it tell me about d? D must be equal to 6. And we get the same answer, of course. So answer 5x plus 2y minus z is equal to 6. So it's just a different approach to the same solution. Instead of rederiving an equation of a plane, I just use my knowledge that any plane has the equation ax plus by plus cz is equal to some number, where ABC is a normal vector. If I know the normal vector, I have this ax plus by plus cz, I should only find out what the number is. To do this, I plug in the point. I know that the point is on the plane, so this equation should be satisfied by this point. I plug in the point, I find out what the number is. Okay, so maybe any questions about the second approach? Okay. A different kind of exercise. I'll give you a plane and ask you to find out what is the normal direction. So what is a normal direction? Normal vector. Y equals to 5. So from the first slide, this equation doesn't look exactly like ax plus by plus cz is equal to d for some a, b, c, and d. But first of all, it is. And second of all, second thing, it is an equation of the plane. If you look at all the points in the space with y coordinate equal to 5, of course they form a plane. Like, if this is the x-axis, this is the y-axis, we make 5 steps in this direction, and here's the whole plane with y equal to 5. So it is a plane. What is the normal direction for this plane? Yeah?
0, 1, 0.
0, 1, 0. So answer 0, 1, 1, 0. Why? Well, because this equation can be written in the familiar form ax plus by plus cz is equal to d. The equation is something times x plus something times y plus something times z is equal to something. Well, what are these numbers? I don't see x, so I write 0 times x. I don't see z, I write 0 times z. I have 1 times y, and on the right hand side I have 5. Once you write this equation in this form, well, it's obvious what is a normal vector. 0, 1, 0. And of course, it confirms our geometrical intuition about what this plane is. The plane is kind of such a plane. A normal vector is something which points towards you in the y direction. So it has x coordinate and z coordinate equal to 0, y coordinate equal to 1. Yeah?
How do you get 1 y then?
Sorry?
How do you get from 1 y?
The 1.
Yeah.
So I want to write y as something times y. So what will be something? 1. Should be 1. Yeah.
On the test, do you want us to use the first solution or alternate technique?
Use the correct solution. I don't care which one. I mean, even if you memorize such a formula, well, I mean, it's for you, but you're welcome. Other questions? Yeah.
Yeah, I'm thinking that this vector, this plane is kind of horizontal kind of plane, and then can we have another answer from 0, 1, 0, maybe 0, 2, 0, 6?
Okay. Yes, so I wrote a normal vector, and of course, a plane defines the normal direction, but multiple normal vectors. So if we're talking about, let's say, this plane, I can have such an arrow, or an arrow which is twice as long, or 5 times as long, and they all will be perpendicular. So every time you have one normal vector, you can multiply it by any number and get it. Other questions? And of course, an equation of a plane is also not unique. Even if you know the plane, it might have several different equations which are equivalent. If you take this equation and say multiply both sides by 5, you are still going to get an equation which describes the same plane, same set of solutions x, y, z. Okay. Other questions? Okay, so let's talk about mutual positions of planes. Let's talk about some special mutual positions. Parallel planes and perpendicular planes. Let's start with parallel planes. So how do we know that two planes are parallel to each other? Well, it's quite easy. If they are parallel, they define the same perpendicular direction, which means that their normal vectors are parallel vectors. So two planes, the planes are parallel when their normal vector stuff. Once again, the reason is parallel planes define the same perpendicular direction, which means they are normal vectors point in the same direction. They are parallel vectors. So there isn't much more I can say about parallel planes. Let's solve an exercise. Find an equation for plane parallel to the plane x plus y minus z equals y, passing So I give you a plane, some plane. This plane probably does not pass through the point 3, 2, 1. You can check. If you plug in 3, 2, 1, you'll get, on the left hand side you'll get 6, 8, 7. On the right hand side you'll get 5. So this point is not on this plane. But we want to find a plane which is parallel to this one, which does pass through this point. So how can we do it? Okay, a normal vector. So first observation, we do know a normal vector to our plane. This plane is normal vector 2, 1, minus 1. So normal vector. It is a normal vector to this plane, but of course it is also a normal vector to any parallel plane to this plane. So if you want a plane which is parallel to this one, it will still have this normal vector. Okay, so we do know a normal vector. We should find out both. So hence the equation that we are looking for is of the form x plus y minus z is equal to d for some number d. And once again, to find out what this number d is, we do the same trick. We know a point on this plane, we can find out what d is. Point 3 to 1 is on this plane. So we get 2 times 3 plus 2 minus 1 must be equal to d. So d must be 7. So our answer is 2x plus y minus z must be equal to 7. So once again, because the two planes are parallel to each other, we know that they share the same normal vector, same perpendicular direction. Once we know a normal vector, we are very close to finding out what is the equation of the plane. We still don't know what d is, but it's very easy to find out. You plug in a point on this plane and find out what d is. example. Planes seven and minus 6x and 1 minus 4z 5 are there. So why these two planes are parallel to each other? Well, what are the normal vectors? For this plane, the normal vector is 3, 1, 2. For this plane, the normal vector is minus 6, minus 2, minus 4. And they are multiples of each other. This vector is just this vector multiplied by minus 2. So they're normal vectors, so they point in the same direction. I mean, one of them is like this, the other one is kind of like this and twice as long, but still they define the same perpendicular direction. So the two planes which are perpendicular to this direction are parallel to each other. On the other hand, say these two planes, y equal to 5 and x equal to 5, are not parallel. Geometrically, it's quite obvious, kind of. Such a plane is not parallel to such a plane, but even algebraically, they're normal vectors. This plane is 0, 1, 0, and is not a multiple of the normal vector to this one, 1, 0, 0. Okay, so maybe any questions about parallel planes? Talk about the different mutual position of two planes, which is also interesting. Perpendicular planes. So of course we know what it means, that the angle between two planes is 90 degrees, kind of floor and the wall, or the wall and the ceiling, or the wall and another wall. The question is how to find out whether two given planes which are given by two equations, are perpendicular to each other. So let's talk about perpendicular planes. So here are two perpendicular planes, the plane of the keyboard and the plane of the screen. Let's find out what being perpendicular to each other means about their normal directions. What is a normal direction to this keyboard? Well, it's something which points up, like this. What's normal direction to the plane of this screen? Well, it's something that points kind of out of the screen in this direction. What can you say about the angle between the two normal directions? 90 degrees. So the conclusion is two planes are perpendicular when course, the result doesn't change if we change what planes we talk about. Like if the two planes are positioned in a funny way like this, still the normal vectors, this one and that one, will still be perpendicular to each other. Okay, so this allows you to solve questions, well, of the type R is a pair of planes perpendicular to each other. So let's solve an exercise. R the planes x plus y plus z equal to 5 and x plus y minus 3z equal to 4 perpendicular to each other. So I give you two planes. I can't really imagine how they look like. I mean, after some thought I might be able to, but still. They are given just as equations. And the question is, are they perpendicular to each other or not? Is the angle between them 90 degrees? How can I check this? Dot product of the vectors. So here's the plane. I know what is the normal vector. What is a normal vector? 2, 1, 1. So it's 2 times x plus 1 times y plus 1 times z. This is the normal vector to this plane. I want the dot product of this vector with the normal vector to this plane, which is 1, 1, negative 3. I want to check, is it 0 or not? Well, let's see. The answer is 2 plus 1 minus 3. And it is indeed equal to 0. So the two planes are perpendicular. So these planes are perpendicular. If you think about it, it is actually powerful stuff. I mean, you can't, well, we didn't even try to imagine how these planes are positioned in the space. But we do know, using very simple computation, how they are positioned relative to each other. They are perpendicular to each other. Maybe another example. Let's go back to these two planes, y equal to 5 and x equal to 5. They are not parallel to each other, are they perpendicular to each other? Well, of course they are. I mean, geometrically one of them is like this, the other one is like this. So they are perpendicular. Algebraically, look at these two vectors, the normal vectors. The dot product is 0 times 1 plus 1 times 0 plus 0 times 0, 0. So they are perpendicular to each other. Okay, let's make a 5. Well, let's say 5-7 minutes break. So we'll start in 5-7 minutes.